Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 18th video lecture, and we are ready to start Chapter 3. Okay, so it begins with a definition. And the first definition is about a convergence sequence. So a sequence, P sub n, in a metric space X is said to converge if there exists a P element of X such that for each epsilon greater than 0, there exists a big N that's a natural number, so big N in J, such that for all n, little n, bigger than big N, then the distance between P sub n and P will be less than epsilon. So that's what it means for a conversion, for a sequence to converge, okay? And we go on to say a little bit more, but before I do, let me give some hint about the idea here. Look, we're saying Pn converges to P, okay? If we can force the Pn's after some point, well, I shouldn't even say after some point. If we can force the Pn's to be arbitrarily close to P, okay, by going far enough along in the sequence. And so that's what this definition gives us. It says, if you give us some epsilon greater than 0, for any epsilon that you give me that's greater than 0, we're going to consider that a distance. And what we can do is by going far enough along in the sequence, there's some spot in the sequence such that from that spot on, the distance from the points in the sequence to P itself will be less than the distance that was given to me. So that's how we're making the P sub n's get arbitrarily close to P. Just as some comments, in this case, we say that the sequence P sub n converges to P or that P is the limit point of the P sub n, and we symbolize this that the P sub n's go to P, or that the limit as n goes to infinity of P sub n equals to P. Okay, next I want to look at some examples. I'm sorry. I want to write down one more definition first. So as a definition, if a sequence P sub n in a metric space X does not converge, then we say the sequence P sub n is divergent, or we say that it diverges. Now let's look at some examples. So if we let piece of n be equal to the sequence 1 over n in R, okay, with our metric space being R with our usual distance formula, that is, the distance between little x and y is equal to the absolute value of x minus y. Then the limit as n goes to infinity of piece of n will be 0. Another example, if we let our sequence piece of n be equal to 1 over n again, with x being equal to, let's say, 0 to 1, including 1 but not 0, with the metric on this space still being the difference between the 2 points inside absolute values, then in this case the piece of n's diverge. Essentially, the piece of n's, 1 over n, should be going to 0, but 0, which is our p, or our limit point for this sequence, is not in the set. It's not in the metric space. So it forces, in this case, the piece of n's to diverge. Let's look at these two examples, even though I've given a description of the second one, a little bit more in detail. Particularly, let's prove the first example converges to 0. So here's the proof of example 1. So how do we show that this piece of n, so again, we're letting piece of n be equal to 1 over n. We want to show the limit as n goes to infinity of 1 over n equals to 0 in this case. Okay, so what we do is we let epsilon be greater than 0 be given. And so from the definition of what it means for a piece of n to converge to p, if for any epsilon that we're given, we need to show an existence of a natural number n such that for all n bigger than or equal to n, the distance between piece of n and p will be less than epsilon. That is, we want n element of the natural numbers such that for all n bigger than or equal to the natural number we found, then the absolute value of piece of n minus p, which in this case would be the absolute value of 1 over n minus 0, will be less than epsilon. So we want 1 over n minus 0 is just 1 over n. Inside absolute values will be less than epsilon. So let's work to see what we want is equivalent to what will prove it. We don't have this yet. We don't have any reason why this would occur. But that's equivalent to wanting 1 over n to be less than epsilon, because actually the value of 1 over n is just 1 over n. And that is, we want 1 over epsilon will be less than n. Okay? So what we want an big N element of the natural numbers such that for all n bigger than or equal to this big N, 1 over epsilon will be less than n. That's what we want. Okay. Well, note, the first thing I would consider is, how do we know there's any natural number that's going to be bigger than 1 over epsilon? Okay? So here's what I'd say. Note, since 1 over epsilon is greater than 0, 1 over epsilon is a real number. Okay? Real number. And 1 is greater than 0, then there exists an n element of j such that 1 over epsilon is less than, let's call this big N, is less than 1 times big N. And this is using the fact that we have from chapter 1, and I mentioned it in our second class meeting as well. Essentially, it gives us, this fact is, that the set of natural numbers are not bounded above, so I can get something bigger than 1 over epsilon. 1 over epsilon isn't bound for it. Okay? So, for all n bigger than or equal to this particular big N, we have that 1 over epsilon will be less than n. That's what we wanted. So that proves it. So I've come up with the big N that works. Now, just to list here on the board, for example 2, one over n diverges in 0 to 1 because 0 is not an element of 0 to 1. That's the reason we get this definition. Now, we're having a discussion here about what it means for a sequence to converge, but let me remind you the definition of a sequence. A sequence, when we say sequence, we mean an infinite sequence, is a function whose domain is the set of natural numbers. As a fact, and I'll show you an example of this pretty soon, a sequence can have finite range. So the output values of the sequence, the points of the sequence, there might be just finitely many of them. So as a definition, a sequence p sub n in a metric space X. Is said to be bounded if there exists a Q element of X such that and M that's greater than 0, such that the distance between P sub n and Q is less than, sometimes books will write down less than or equal to, but here we're going to say less than M, and this is true for all n element of J. So this distance is going to be less than M for all the terms of the sequence. Okay. All right, well, let's look at some examples then. The first one, so we look at the sequence -1 to the n runs from 1 to infinity. What's this equal to? Well, this equal to -1, 1, -1, 1, and so forth forever. And so here's what we can say about it. This is a sequence in R, and here we're thinking of that having the metric, the usual metric. The distance between x and y being equal to absolute value between x and y. Okay? So this is, the sequence is a sequence with finite range okay. It is bounded you can use as your Q 0 and the distance between each one of the output values, each one of the terms of the sequence, and 0 is going to be less than 2, for instance, because they're all 1 unit away from 0. It's bounded. N is divergent. So there isn't a single real number for which this sequence gets arbitrarily close to. Before I move on, you see, there is no number such that from some point beyond in the sequence, all the terms of the sequence are, from that point on, are arbitrarily close to that particular number. Because the sequence just keeps bouncing between -1 and 1. Let's look at another example. So another example is if we look at the sequence that's 1 to the n. Okay? And that sequence is the sequence that is just constantly 1. That's a sequence in R. Again, we're thinking of R having the usual metric. Okay? That has a sequence that has finite range. There's only one number in the range, 1. It's bounded. If you let Q be 0, all the terms of this sequence are within 2 units of 0. And converges. What it converges to is 1. Third example is our 1 over n, which is equal to 1, 1/2, 1/3, and so forth. We think of it again in R with the usual metric, okay? is a sequence that does not have finite range. It has infinite range. And it is bounded. And converges. We've already seen it converges to 0. Let's look at one more example. If we look at the sequences just in R with the usual metric, what's that equal to? Let me back up. What is this? This is 1, 2, 3, 4, forever. Is a sequence whose range is infinite, is unbounded, and is divergent. Does not converge. All right, let's get to some facts about sequences. So here's a theorem that has 4 parts that we will prove. So we'll let P sub n be a sequence in a metric space X. Then the first thing that we have is that P sub n converges to P which is known to base, if and only if every neighborhood of P contains Pn for all but finitely many n's. For all but finitely many n's. Part B, if P is a point in X and P prime is a point in X, and if P sub n is a sequence, converges to P and to P prime, then P has to be equal to P prime. In essence, this part is saying, if you have a sequence that converges, what it converges to is unique. Okay? You can't converge to more than one thing. Part C is if Pn converges, then Pn is bounded. And then part D, if E is a subset of our metric space X and P is a limit point of E, then there exists a sequence, P sub n, that's in E that converges to P. So those are the four things we want to prove. So here's the proof. Proofs. For part A, it was an if and only if statement. So in this direction, we're going to let P sub n converge to P. And what we want to do is show that every neighborhood of P contains all but finitely many of the sequence points. Okay, so we're going to let n sub r of P be a neighborhood of P. Since P sub n converges to P, that means there exists a natural number, we call it big N, such that for all natural numbers n greater than or equal to this big N, that the distance between P sub n and P, well, the natural number that I picked depends on what epsilon it was given to me. Well, I'm going to say, let's let epsilon be r, the radius of this neighborhood. And so given this radius, this epsilon greater than 0, this radius, there is some n natural number, such that for all natural numbers bigger than that, bigger than or equal to that, the distance between Pn and P would be less than r. Okay? So that means that n sub r of P, that neighborhood, remember, that neighborhood of P consists of all points whose distance from P is less than r. That would consist of all the Pn's. So this neighborhood would contain all the Pn's where the n value for the Pn is going to be greater than or equal to n. So the only ones that it might not contain are the P sub n's where the n value is less than this capital N. And there are only finite many of those. So here, n sub P contains Pn for each n bigger than or equal to this big N. So I should say, so so the neighborhood, I should say, contains of the p-ins. And that's the proof for part A. It may contain them all, okay? That neighborhood might. If it does, there's only finite and many not contain, 0. All right, we have, and that isn't the end of the proof. I made a mistake. We have to go in the other direction. Okay, so in this direction for part A, we suppose each neighborhood of P contains all but finitely many of the P sub n's. So here's what we're going to do. We're going to show that P sub n converges, the sequence P sub n converges to P. How do we do this? Well, we let epsilon be greater than 0 be given. What do I need? We need an n that's a natural number such that for all n bigger than or equal to this big N, the distance between P sub n and P will be less than epsilon. Well, here's what we do. We consider the neighborhood of radius epsilon about P. Okay. So this neighborhood, by assumption, contains all but finitely many of the PNs. Okay. Let's say the ones that it doesn't contain, let's call those out. Let's give them a designation. Say P sub n sub 1, P sub n sub 2, all the way up to P sub n sub j. Okay. So these are the ones that are not contained in the neighborhood of radius epsilon about P. So if we let big N equal to the maximum of the n sub 1, n sub 2, up to the n sub j, then, for all n bigger than or equal to n plus 1, okay, P sub n, those terms for n values bigger than n plus 1, will be an element of this neighborhood. And this was epsilon. So, for all n bigger than n plus 1, okay? So this n plus 1 is like my n in the definition for convergent sequence. The distance between P sub n and P will be less than epsilon, and that's the proof. Well, let me write a conclusionary statement. So that means that the P sub n is converged. That's the proof of part A. For part B, so part B said that if P sub n converges to P and P sub n converges to P prime, then P and P prime have to be the same. So let's prove that. So let P sub n converge to P and P sub n converge to P prime. We want to show that P must be equal to P prime. Well, we're going to do this by supposing not. Suppose that P is different than P prime. Well, then the epsilon we're going to get involved from our definition of convergence per sequence is the distance between P and P prime. And that can be an epsilon because it's going to be greater than 0 since these two points in X are not the same. So their distance is greater than 0. And that's going to act as, that distance is going to act as an epsilon for us. All right, since P sub n's converge to P, there exists an n sub 1 element of the natural numbers such that for all n bigger than or equal to n sub 1, the distance between P sub n and P will be less than 1/2 the distance between P and P prime. And similarly, since the Pn's also converge to P prime, there exists an n sub 2 element J, such that for all n bigger than or equal to n sub 2, the distance between P sub n and P prime will be less than 1/2 the distance between P and P prime. Okay. We want both of these things to happen simultaneously, and these statements say, hey, if you push in the sequence to the nth position, okay, or the n sub 1 position, then from then on, all the terms of the sequence will be within this radius of P, be in this distance of P. But if you push to this spot in the sequence, n sub 2, then all the points of the sequence from that point on will be within half of this distance from P prime. We'd like for both of them to happen simultaneously, so we really need to push to the maximum of those spots in the sequence. So we let n equal to the max of n sub 1 and n sub 2. Then, for all n greater than or equal to n, we have P sub, or the distance between P sub n and P is going to be less than 1/2 the distance between P and P prime, and the distance between P sub n and P prime is going to be less than 1/2 the distance between P and P prime. So, if we look at the distance between, here I'll start it this way. So for all n bigger than or equal to big N, the distance between P sub n and P plus the distance between P sub n and P prime will be less than, well, this is less than 1/2 this distance, this is less than 1/2 this distance, so adding them will get less than just this distance. But that violates a characteristic of being a metric. This is impossible. Okay? This contradicts d of x comma y being a metric. So we made an assumption that was incorrect, and so that means that P had to be equal to P prime because we assumed that they were different, but we got a logical inconsistency. And so that is part B. For part C, remember here we're trying to show that if you're a convergent sequence, then you're bounded. So we'll let P sub n be a convergent sequence, meaning that it converges to P, converges to some point. We want to show that this sequence, P sub n, is bounded. And that means we're going to have to find, some point in x and some positive number such that for all the terms of the sequence, P sub n, their distance away from that point is going to be less than that positive number. Okay, so since P sub n converges to P, then there exists an n, that's a natural number, such that for all n greater than or equal to big N, the distance between P sub n and P will be less than 1. So 1 is acting like my epsilon. For 1, there's some natural number such that for all n bigger than that. So there's some spot in the sequence such that for all spots bigger than that, the terms of the sequence in those spots, their distance from P will be less than 1. Okay. So here's what we do. We let m equal to the maximum of the distance between P sub 1 and P, the distance between P sub 2 and P, all the way up to the distance between P sub, it would be n minus 1 in P, and then one more thing, 1. Then, for all n that are in the natural numbers, the distance between P sub n and P will be less than m. Here, let's say less than or equal to n plus 1. Let's do that. Thus, P sub n is bounded because here's a positive real number that all the terms of the sequence distance from this fixed point is less than that real number. So that ends part C. And now for part D. Let's remember, what we're trying to show here for part D is that if P sub n converges to, if we have E is a subset of X and P is a limit point of E, then there's some sequence in E that converges to P. Okay, that's what we're trying to do. So, for part D, we let E be a subset of X and P be a limit point of E. We want to form so we want to create a sequence P sub n that's a subset of E such that, P sub n converges to P. Okay, so how are we going to construct this sequence? Well, since P is a limit point of E, that means that every neighborhood of P intersects E at some non-P point. So I'm going to say there exists a P sub 1 element of E such that the distance between P sub 1 and P is less than 1. Similarly, there exists a P sub 2 element of E such that the distance between P sub 2 and P is going to be less than a half. So we think of the radius of the neighborhood of P being a half. And because P is a limit point of E, there's got to be some non-P point in E that is in that neighborhood. So its distance from P has got to be less than half. That's P sub 2. We're going to continue this pattern. Let me write it one more, or just in general. In general, there exists a P sub n element of E such that the distance between P sub n and P will be less than 1 over n. In each case where P sub n is different than P. Thus, we have created a sequence P sub n that's a subset of E. Each one of its elements is in E. What we need to do is we need to show that this particular Pn converges to P. Okay? So here, we let epsilon be greater than 0 be given. Okay? Since there exists an n element of the natural numbers such that 1 over epsilon is less than n, then for all n bigger than or equal to this big N, one over epsilon will be less than n. So that says for all n bigger than or equal to this big N, 1 over n is less than epsilon. So for all n bigger than or equal to this big N, the distance between p sub n's and p will be less than 1 over n, which is less than epsilon. And so that shows that p sub n converges to p. And that concludes this theorem. Okay, ladies and gentlemen, I believe that is enough for this lecture. Thank you very much.